Hi, my name is Yunfei He, and today I'm going to give a short introduction on semiconductor heterostructure laser diode. To discuss the semiconductor heterostructure laser diode, we need to first introduce what a laser is. Laser is short for the light amplification by stimulated emission of radiation. This concept was first conceptually brought up by Albert Einstein in the paper on the quantum theory of radiation in 1917. Based upon probability coefficients, also called Einstein coefficients uh, for the absorption, spontaneous emission, and stimulated emission of electromagnetic radiation. The theory of the stimulated emission is when we have a particle in its excited level, if we incident the photon with exact same energy as the energy gap between two levels, which is delta E here, it will stimulate the excited particle to fall back to the ground state and emitting a photon. Well, in 1960, the first functional laser constructed by a flash lamp pumped synthetic ruby crystal to produce red laser light at 694 nanometer wavelength came up. From the figure, we can see that they shine a light at a wavelength of about 550 nanometer to the ruby, and the chromium ions are excited to the higher state, which is the F2 state here. Then after non-radiative transitions, it follows decay of spontaneous emission, which emitting light at the wavelength of 694.3 nanometer and 692.2.9 nanometer, which is showing like this spectra in the figure 2 here. Well, in 1962, Marshall Nathan published the first diode laser based on the gallium arsenide p-n junction. Instead of light inducing, the semiconductor laser diodes are electrically pumped. Like forward electrical bias across the laser diode will cause two charge carriers, holes and the electrons, to be injected from opposite side of the p-n junction into the depletion region. This injection would increase the possibility of the recombination of the electron and holes, which truly is the electron falls back to valence band from the conduction band, which will emit photon if the device is a direct bandgap semiconductor. For the first laser diode, it can only operate under a lower temperature that's around 77 K with a threshold current of 10 to the power of 4 to the 10 to the power of 5 ampere per square centimeter. The homojunction laser diode is a no-go operating in the room temperature. With this big challenge, it soon hit the engineers that there was an opportunity to introduce heterojunctions for the diode. So 1 year later, the first heterojunction diode with a threshold current of 10 to the power of 4 ampere per square centimeter, which is 10 times lower than that of the homojunction diode, that one was invented. It showed a great potential for the semiconductor heterostructure laser diodes. And now let's discuss some main characteristics we need to consider in the laser. First is to achieve the photon emission, we need to have a way to get enough particles at the excited and particles at the excited energy level. Like for instance, in our circumstances, the electrons at the conduction band. With the density of the excited particle greater than that of the ground state particle, the rate of emission would be greater than the rate of absorption. Then we can eventually generate photon through the recombination process in the semiconductor. Well, in the heterostructure laser diode, double heterojunction laser diode for example, with a narrow band gap active layer between the p-n junction, the narrow band gap helps to confine the electrons in holes in this region. This is because the electron would prefer to stay at the lower energy state, which means stable for it. Sorry. This confinement results in a decreases of the threshold current, which is one of the challenge through the laser diode history. We can notice that for the evolution of the threshold current of semiconductor lasers, um, the introduce of the heterostructure, the double heterostructures here, um, it made a really significant changes on the threshold current over the years of modifications. And the gain medium here is to put into an excited state by an external source of energy. Well, in the semiconductor laser diode, we applied the junction to forward bias to inject the carrier we need for the photon emissions, which is much easier or more accessible than that of using light to excite the particles. And the stimulated emission is not enough to have a laser. We need to make sure the photon generated could be resonant, and thus we could have a go for this laser amplifier amplification. There are a lot of designed structures for laser to get resonance, such as a really simple FP resonant laser, or external cavity laser, or distributed feedback laser, or distributed Bragg reflector laser, etc. These structures will be discussed in detail in ESE 673 in spring. Uh, let's bring it back to the semiconductor heterostructure laser dial here. The heterostructure also have a superior lateral confinement for not only current and charge we mentioned before, but also photons, because the blocking layer can have a significantly higher band gap than the active region. Like in addition to better confinement of current and charge, the higher band gap has a lower refractive index, which can produce strong index guiding in the waveguide. This photon confinement will result less loss, less loss during the resonant, which would also reduce the energy required for the laser. And furthermore, people now introduced a short period superlattice in the active layer, like the figure 8 shown here. They succeeded in obtaining the desired index profile in the waveguide region and creating a barrier against the motion of these locations into the active zone. Therefore achieved excellent surface morphology simultaneously with a high internal quantum efficiency. With the laser being applied in real broad areas such as telecommunications, media, medical uses, and nanotechnology, having high quantum efficiency in low cost laser is always the goal to design the laser. Excuse me. The semiconductor heterostructure laser diode gave a solution for semiconductor laser working at a high quantum efficiency with low threshold current under the room temperature. We show uh, a bunch of different designs here for heterostructure semiconductor laser diode. And with the application of superlattice mentioned above, it actually brought us to the theoretical limit of the threshold current, one of the most important parameters we discussed before. Uh, it always comes to more parameters we need to consider for the trade-off during the design of a semiconductor laser diode. The first one is the modulation speed. During some integrated photonics designs, we're not only looking for a threshold current for a laser, but also the accessibility to modulate this signal for the information to transport to vary and vary. Yeah. The designed structure nowadays it has a high capacitance that contributes to the total capacitance of the laser, which will limit the modulation speed. And the second is the energy cost. This might sound contradictory, but the designed junctions always meet an issue of the leakage current, and some of the laser diode could be very leaky and allow current to flow along the edge of the active layer around the p-in junction at high power, and specifically at high power. The third one is the temperature. The semiconductor laser is greatly dependent on the temperature. It might not give a consistent result under various temperature circumstances. These could be challenges for the future designs. That's all for my presentation. Thank you all for listening.